Hi everyone, in this video I will discuss AVL trees under the data structures and algorithms for week 9. So here's what you'll find in this presentation. Analysis of a tree-based algorithms, BST, and operations in BST, binary tree operations, and AVL tree rotations. So let's start with the analysis of tree-based algorithms. Binary search trees. So a binary search tree is a special search tree that satisfies the following property. So before we go on to the property, let us define first what is a search tree. A search tree is a tree data structure used for locating specific keys or data from within a set. So remember your linked list topic from our previous module. Each node has their own data. So in binary search tree, we're also locating those data, and the property that is used by the binary search trees is that the value of every node is greater than or equal to the values of the nodes in its left subtree and is less than or equal to the values of the nodes in its right subtree. In order to visualize this property of a binary search tree, let us have this example. Suppose that we have this tree. All the values assigned to each nodes are based from the property of a BST. So as you can see here, if we check the root node, its value is 6, and all of its left subtree node, okay, all the nodes on the left subtree is less than the root, okay. Let's say, for example, we go down here on the next node, the value is 4, so 4 is less than 6. Even though we go through the rest of the nodes from the left subtree, all of its value is less than the root, which is 6, okay. And then all the nodes on the left subtree going down to 8, and then 7, 9, 8, and 9. So all of the values of this left subtree is greater than the root. Okay. So if we consider this, let's say for example, this node as the root node, all the left subtree or all the nodes in the left subtree of its left subtree is also less than the root, as well as in its right subtree, it's greater than the root. Okay. Okay. So same goes for the right subtree. Now, with this property, it is no longer necessary to examine every node in the tree when searching for a value. Suppose that we have, or we need to search for 7 in this tree. Okay, so we need to search for node with a value of 7. Okay, so we will start with the root node. So from the root node, we will compare if the value inside the root node is the number that we're looking for, which is 7. Okay, so since 7 is not equal to 6, obviously, so we go to the right subtree. Okay, so 6 is less than 7, and we all know that the property of a BST is that all of the nodes in the right subtree have a value or data that is greater than the value in the root. Okay, so with that, we're not going to examine this part of the tree. Okay, so we'll just focus all the way down to the right subtree, going to our next node, which is 8. So is 8 equal to the number that we're looking for, which is 7? So it's not. So we will compare if this is less than or greater than 8. So is 7 less than or greater than 8? So the answer is it's less than. Okay, so if it's less than the root, or let's say the current node, so I mean to say we're going to go to the left subtree. Okay, going down to the left, so we have here another node with a value of 7. Okay, so 7 is equal to 7, so I mean to say this is the node that we're looking for. Okay, so it only takes a few steps to reach this node, and we already expand this tree until we reach this particular node without having to examine this left subtree. So here are the other operations in the binary search tree. We have the find or search, find min and find max, insert, and also the delete. Okay, so let's say for example we want to find 4 in this tree. So using the property that we have used a while ago, so we will just compare if 4 is greater than or less than 6 from its root. Okay, so Since it is less than, we go to the left sub-tree and then compare if 4 is equal to 3. So it's not. And then let's check if it's greater than or less than 3. So since 4 is greater than 3, so we go to the right. And then the next node contains 4. So is 4 equal to 4? Since they are equal, then that's the time that we stop searching and return this node. Okay? Now, for inserting class, we just need to use the property that we have used a while ago. Okay? And look for a node that points to null. Okay? So, going to our, from our node 6, so is 5 greater than or less than 6? So, this is less than. So, we're going to go down to the left sub-tree and then compare 5, it's greater than 3. So, since 5 is greater than 3, so we go to the right sub-tree. Okay? And then check if this next node is greater than or less than 5. Okay? So, since 4 is greater or is less than 5, so we go to the right sub-tree. And since this right sub-tree points to null, so that's where we put or insert the 5 as another node. Okay? So, this will be node 5. Okay? Now, in terms of deletion, so again, we're going to use the property. So from here, from our root node, we will just go to the left sub-tree since 2 is less than 6. And then compare it again. So since 2 is less than 3, it's not the number that we're looking for. So we go to the left again. And then since we have located our node that we have to delete, so that's the time that we have to remove it and then change the pointer of this tree to its successor node, which is 1. Okay? So for the case of 2 having 2 children, let's say for example we have another node here. Say we have another node here. Example, this is 3. Okay, so since this is 3, we're just going to remove this, and then this 1 here will be replaced on our on the location of 2. Okay, so that's it. So next, find min. You just need to go to the left subtree. Okay, you don't have to go to the right subtree. You just always go deep down to the left subtree. So from here, go to the left, left, and then left until no more nodes is available. Just in case that there is a node pointing to the right, you don't have to go there because we're finding the min. Okay? So you need to always traverse to the left. Okay? In case of you have to find the maximum value of a tree, so it's just the opposite of find min. You always go to the right subtree. Okay? And here we found 8. Okay? So that's it. Now what happens when the input comes into the tree already sorted? Okay, so remember that class, each time that we insert a value, it's not always it's not always on as a one process insert that we're going to write this as 1. Okay, we insert these values one by one. Okay, so for example, we need to insert 1, so this is 1. We need to insert 2, so that's 2. We need to insert 3, and then we need to insert 4. Okay, so that's one by one insert. You don't draw it based on your guess what would be the ideal tree for this. Let's say for example you want to draw 1 2 3 4 something like this 2, and then we have 1, and then we have 3, and then we have 4, or any other forms of a tree. Okay, so you need to insert it one by one. So just like this. Okay, so here we have a skewed tree. Remember our topic about binary trees? So this is a skewed tree. Okay, in AVL, this is the worst case scenario. If you are trying to insert a value, let's say for example 5, you need to traverse from the right subtree, from our root to our right subtree, deep down to node 4. Okay? Though we all know that we could rewrite this tree into something like 2 as the root node, and then the siblings are 1 and 3, and then under root node 3 is 4, and then that's the time that we reach 5. Okay, but here in this skewed tree, which is the worst case, we have to go all the way down from the next node to node 3, node 4, and then until we reach a node that points to null. And that's where we're going to input or search or insert for 5. Okay? So with that, in order to solve this problem, we need to implement a tree, a self-balancing tree. Okay? So here we have that kind of tree, the Adelson-Velsky and Landis tree, or AVL tree. So an Adelson-Velsky and Landis or AVL tree is a BST with a balance condition. Okay? So this balance condition states that the AVL tree, it ensures that for every node, the height of the left and right subtrees differ by at most 1. So remember your lecture from our binary tree? So we are going to solve the difference between the height of the left subtree and the right subtree. If the difference is 1, then that's a balanced tree. But if it exceeds 1, let's say for example 2 or 3, then that's the time that we have to rebalance the tree. Okay? Let's say for example we have this. So since this left subtree, the height is 1, obviously. So this is 1. And then the right subtree, which is 0. So 1 minus 0 is 1. Okay? So meaning to say the difference between these two subtrees is 1. So meaning to say this is balance. Okay? Next. So from our previous example, so this is a balanced tree. Okay? So the height is 2. And then this one is 0. And then going to the to its parent, so it's 1. So 2 and 1. So this is still balanced. Okay? So how about the previous example of a skewed tree? How are we going to balance this this tree? Okay. Suppose that we are going to insert 1, 2, 3, 4, 5 now. Okay. So there's a 5 here, missing a node. So as I have said a while ago, we're going to insert each node one by one. So we could fix this by rotation. So the rotation is it can be in any form. Okay. So left rotation, right rotation, left rotation, left right rotation, or right left rotation, depends on the situation. Okay? So in AVL 3 it supports the rotation. Now let's try to simulate how are we going to solve for the this skewed tree. Okay? Suppose we have this sorted value. We're going to insert this sorted value to the AVL tree. Okay, so insert 1, insert 2. So the height of this tree is 1, then this is 0. Next, so this would become 2, and then this would become 0. Okay, so 1, 2. So this is 2, this is 0. Okay. So since we have a difference of 2, and we all know that a balanced tree should have a difference of at most 1 for the left subtree and the right subtree, we need to rebalance this. Okay? In order to balance that, we need to make a left rotation. Okay? So from here, from our 2, we just need to make it as the root node. It's like pulling a string that is attached from 2. Okay? It's like this. Okay? Let's say we have a string attached to 2, and then we need to pull this string until it reaches the top of the node. Okay? Now we have a balanced tree here with a difference of 0. Okay? So this is 0. So if this is the right subtree, the left subtree, so this is 0. It doesn't have a child node. This also has no child node. So 0 and 0. Okay? So next, let's try to insert 4. So this is 0. This is 1. So this is 0. Again, this is 0. And then this is from the deepest node 1, 2. So this is 2. Okay? So the difference of these two subtrees is 2. So we need to make some rotations here wherein it occurs an imbalance. So we just need to rotate this part in order to make it balance. Okay? So with that, again class, we're going to pull a string again here at number 4. Okay? So let's try this. Okay, so that's it. Until it becomes a balanced tree. Okay? So if we try to compute this, so the left subtree is 0, the right subtree is, so from the deepest node, and then 1. Okay? So this is already balanced. So this is a balanced tree. Okay, so this is the left rotation, the right rotation. Okay? So as you can see here, we have here as the root node the 1, going to the right 2, going to the right again 3. Then as you can see here, we pull the string from 2 to make it the root node. Okay? Now here the root node is 3. This is the greatest, it has the greatest value. So going to the left is the next node, which is 2, and then 1 as the lowest value of the node. So from here, we're going to pull the string to the right to make it something like this. Okay, so this is the right rotation going to the right, so that's why it's right rotation. Now we have also another variation of rotation, which is the left-right rotation. Okay, suppose we have these values, so let's validate if this is this is possible. Okay, so the entries are 5, 2, and then 4. Okay, so we're going to insert 5, and then next is 2, so going to the left, so this is 2, and then we need to insert 4, so 4 going to the left of 5, 4 is greater than 2, so 4 is going to the right of 2. So this is a valid entry. Okay, so let's try this one. So if we have this tree, so we need to perform a left-right rotation. So let's say, or suppose we have another node here, which is the root node. Let's say 6, and then we have here a single node, which is 7. Okay, so the height of this tree is 2. Okay, the height of this tree is 2. So from the deepest node, 1, 2. And here, this node here only has 0 nodes. So this is of height 0. Okay? So there's an imbalance between these two. So we need to balance them on which part the tree has become imbalanced. So this is where the tree has become imbalanced. Okay? So with that, the shortcut method for this is to get the node 4 onto the top of these two nodes. Okay? So how did it happen? So let's try to analyze this node here, this two. The original form is this one, and then this is the final outcome. Imagine that these two here, we need to pull it down and then put 4 onto its place. So that's the left rotation. Okay? So this would become 5, and then 4, and then we have 2. And based from this formation, if you have, if you still remember the right rotation a while ago, this is the rotation, the right rotation. If you have this form, you could make a right rotation from this set of nodes. Okay? So since we have this form, 5, 4, and 2, we just need to perform a right rotation. So that's why it becomes something like this. Okay? So from here class, we just need to pull 2 down to the left and then replace it with 4 to make it something like a right or a left skewed tree. So 5, 4, and 2. And then once you're done with making this as a left skewed tree, you can perform a right rotation to make it something like this. Okay? So we also have a actually this is a right left rotation. Okay? Not a left right rotation. This is a right left rotation. Right left rotation. Okay? So just like our previous example, we just need to perform a left rotation and then right rotation. Okay? So there's a line here. I forgot to put some lines here. Okay? So from this node, we just need to pull 3 down to its left subtree, which points to null, and then replace its previous location with the node 2. So to make it 1, 2, and then 3. Okay? And then once you're done transforming this into a right skewed tree, you just need to perform a left rotation. Okay, so that's why it's called the right left rotation. Okay, so that's it, class. Thank you for listening, and I hope that you understand those rotations in our AVL tree. Thank you, and God bless.